Welcome to the Physics Division at Argonne National Laboratory. Thank you for taking the time to come visit us today. More than 50 years ago now, the founders of Argonne National Laboratory thought that it was essential that a group of scientists at the lab would be wondering about the fundamental properties of nature. And that's how the Physics Division came into being. And our mission is to study the nucleus. At the center of every atom is this tiny object made of protons and neutrons that is the nucleus. It's tiny, all right, but it is the real core of matter. To study it, we use a number of instruments, like the Atlas Accelerator that you will see during your tour. Now, the research we do is fundamental in nature, but it has, of course, a large number of applications for the benefit of society. So again, welcome, and I hope you will enjoy the tour. Now, Dr. Guy Savard, who is the scientific director of our Atlas Accelerator, will tell you more about the members of the division.
Hi, welcome to the Physics Division. Welcome to the Atlas Accelerator. I'm Guy Savard. I'm the scientific director of Atlas, and I'm happy to have you here today. What we do here is trying to understand the nucleus, trying to understand its structure, trying to understand its role in the cosmos and how we got here, trying to understand the various applications and develop new applications for it in society. We do this through 5 main activities: theory, where we try to develop a consistent predictive theory of the nucleus. We do this using the very large computing capabilities which are available on site here at Argonne. The Medium Energy Group, which tries to understand through various experiments at different facilities around the world the component of the nucleus, the neutron and the proton, and their basic interaction. We have the Low Energy Group, which works mostly on the facility here, Atlas, and they look at heavier nucleus, their complex nature, trying to understand the role that they play in the creation of the heavier element, from the seed of the Big Bang, the hydrogen and helium, to everything else that we have around us, which has been created in stars through nuclear reactions. We have the Atlas Operation Group itself, which runs the facility. This is a user's facility used by of the order of 1,000 users, running 7 days a week, 24 hours a day, 50 weeks a year or so. It's a busy place. And it runs experiments for the university community in the US, other laboratories in the US, and a large community outside of the US, which is coming here to use the unique capabilities that we have. And in addition, we have a research and development group working on superconducting RF, superconducting cavities, new accelerator technologies, which are used to keep up to date the facility here, develop new capabilities for the users and also for other facilities outside. I hope you will enjoy the tour of Atlas. You will see the large equipment that we have in place to do this physics. We find it very exciting. I hope you will find it too. Thank you.
Hi. Here at Argonne, safety is incorporated into everything that we do. In fact, it's so integral that we actually have a program for it. It looks complicated, but it really comes down to just doing what you normally do. Think about the hazards of anything that's going to happen and take care of them. Not only are we worried about our own safety, we want to make sure that the community is safe and the environment doesn't get harmed. And everything we do strives for that goal. Why? Well, first of all, it's just a good thing to do. Second, we live there. Most of us are living in the communities around Argonne. As you go through the building today, you're going to see several signs that have caution or warning on them. But be assured, everything that you're going to be going through today is perfectly safe. We hope you have a good trip, we hope you have a very interesting trip, and we hope you have a safe trip. Thank you.
Hello, I'm Craig Roberts, leader of the Theory Group in the Physics Division at Argonne National Laboratory. The Physics Division Theory Group has a long and distinguished history. For example, it was home to Maria Mayer, one of the few women to receive the Nobel Prize for Physics. and her work in 1963 was on the shell model of nuclear structure. To study nuclear structure is to delve deeply into the nature of matter in order to discover how the nuclei of the atoms which compose all visible matter in the universe, and our bodies as well, are formed and interact. Many of them remain whole. Those in our bodies, for example, are generally stable. Other nuclei, however, are unstable. This makes them useful in medicine. For example, positron emission tomography relies on the beta decay of nuclei in order to provide a three-dimensional picture of functional processes in the body. Nuclear structure remains a key focus of both experimental and theoretical research in the Physics Division. To get a picture of the experimental program, I encourage you to tour the division's ATLAS facility. Members of the theory group have continued to make enormous progress in unfolding the structure of nuclei. Indeed, two of my colleagues, Steve Piper and Bob Wieringa, were awarded the 2010 Bonner Prize, the American Physical Society's highest honor in nuclear physics, for developing the theory of nuclear forces and novel computational methods to calculate the properties of nuclei. Experimentalists and theorists in the Physics Division are also heavily involved in research that probes into the very origin of mass and matter itself. The Large Hadron Collider at the European Centre for Nuclear Research is searching for the Higgs boson, and perhaps they've found it. However, the Higgs field is responsible for just 2% of the mass of visible matter in the universe. The remaining 98% is produced by remarkable phenomena within the fundamental theory that generates the nuclear forces. This theory, called quantum chromodynamics, discoveries within which were awarded with the 2004 and 2008 Nobel Prizes in Physics, describes the interaction between quarks and gluons. These particles are fundamental. They have no internal structure that we can yet discern, and their properties are the most interesting part of the standard model of particle physics. The division has an exhibit that describes how we try to untangle their web of complex interactions, which I encourage you to visit. There you can also speak to experimentalists and theorists from the Physics Division who are involved in the process. So, welcome to the Physics Division. I'm certain you'll find the visit worthwhile.
Hi, welcome to the Atom Trap Laboratory. I am Zhentian Liu.
I'm Wei Zhang.
We are Atom Trappers. So here's an atom trap. We send in the atoms on this end. They rush along the pipe towards the trap.
Here we're sending a laser beam to push on the incoming atoms to slow them down. By the time the atoms get here, they're already slowed and tired and can be captured into a trap formed by 6 laser beams. The atoms in the trap appear as a bright dot and can be readily detected with a CCD camera. When running the experiment, we can actually see the image of a single atom appearing and disappearing here on the screen in real time.
So in this laboratory, we solved a long-standing challenge posed by Swiss scientists back in 1969. They wanted to find a way to detect radioactive isotopes of krypton and argon and use these isotopes to trace the movement of groundwater and the circulation of ocean currents, and to determine the age of polar ice. These radioactive atoms can tell us a lot about the environment. So this dream of radiokrypton dating has been pursued for the past 4 decades. But detecting these tracer isotopes has been a great challenge for all these years because the atoms are so rare. For example, in the air, there's only one krypton-81 atom out of every 10 to the 18th atoms. That's 1 followed by 18 zeros. 1 out of 10 to the 18th. That's how rare it is. And using this trap right here, we finally figured out how to count these special atoms.
We've analyzed samples from the Sahara Desert, from Yellowstone National Park, from the nuclear waste storage site in New Mexico, from the outback of Australia, and from Antarctica. Here in this laboratory, we are analyzing water samples from all over the world.
Welcome to Helios, the helical orbit spectrometer. Helios is one of the experimental devices in use here at Argonne, and it's the first of its kind in the world. What makes Helios so unique is the large MRI magnet you see here behind me. The magnetic field produced by Helios allows us to make high-resolution measurements of nuclear reactions. These measurements allow us to study nuclear structure and nuclear astrophysics. The unique nature of the Helios spectrometer allows us to make higher resolution measurements than anybody else in the world.
So, welcome to the ATLAS facility. ATLAS is an acronym that stands for the Argonne Tandem Linac Accelerator System. It is a national user facility for research, mostly in nuclear physics. ATLAS is the world's first application of the use of RF superconductivity. That technology was largely developed here at Argonne in the 1970s, and ATLAS was the demonstration project that showed that we could in fact use RF superconducting devices to accelerate ions. As I said, ATLAS is a national user facility. That means that scientists from all over the world can propose experiments and have them approved for research here. And they will use our high velocity ion beams, which consist of any species from protons through uranium to irradiate samples that they will place in the beamline and look at what happens. In many ways, the analogy of doing nuclear physics research is similar to studying how a watch works by using a hammer and striking it and seeing what flies out. What you'll see at ATLAS then is the equipment and technology that produces these high velocity beams for the research program. And then you will also go out to the experimental areas and you'll be seeing some of the equipment that is used by researchers to make the detections of what happens in these violent collisions. Because we believe that in the Big Bang, none of the material that you see around here or on the planet Earth, largely none of that existed from the Big Bang. It only happened after stars began to form and burn the hydrogen and helium that was part of the Big Bang process, that then we began to see carbon, oxygen, nickel, silicon, gold formed. And our studies of nuclear physics are an attempt to understand how that happens in stars and how we got here. So we hope you'll enjoy your walk and visit around ATLAS and learn a great deal about how we do research here. Thank you.
Welcome to the ATLAS Accelerator Control Room. ATLAS operates 24 hours a day, 7 days a week.
Meet our operations crew. 7 of us provide accelerated particles for scientists from all over the world to come here and use.
Thank you for coming and visiting ATLAS.
Hello, my name is Michael Kelly, and I'm an SRF scientist here at Argonne National Laboratory. What you're looking at behind me is a 15-foot long section of superconducting particle accelerator that will be installed here at ATLAS in 2013. This device is cooled to 4 degrees Kelvin, just above absolute zero. That's minus 452 degrees Fahrenheit when it's operating inside the superconducting particle accelerator. We also build the world's best room temperature copper accelerators. All of these devices are designed and built at Argonne and installed here at Argonne and other facilities around the world. Please come see all of this at the Argonne Open House. Thank you.